So in the previous video, we looked at the property change, which is the entropy change of pure substances, and why it is sometimes advantageous to use TS diagram instead of TV diagram, which we have been using so far, because we haven't done entropy so far, right? But now we know that TS diagrams are cleaner and give more information and more insight than TV diagrams, and so it is sometimes more advantageous to use TS diagrams. There is one more important reason why we use TS diagrams instead of TV, and that is what we are going to discuss in this video, right? So recall that ds, which is the differential change in this entropy, is equal to delta Q by T internally reversible, right? So if we had an internally reversible process and we did delta Q by T for that process, that would be equal to ds, which means that I can write delta Q internally reversible is equal to T ds, right? And I can therefore write Q internally reversible is integral T ds, right? That is, the heat added to a system is during a process is equal to the integral of TdS, and this immediately looks like something that we have seen before. For example, integral PdV, and integral PdV happens to be the reversible work done by the system, right? And so, and that was very convenient because that was just area under the curve when we plotted it in a PV diagram, right? So similarly, if we plot a TS diagram, then the area under the TS diagram happens to be equal to the internal to the heat added in an internally reversible process. This does not mean that the actual heat added is equal to this value, but if we followed an internally reversible process, then the heat added would be equal to the area under the curve in a TS diagram, right? And because all diagrams that we plot are inherently internally reversible, because it's not possible to plot irreversible processes on a 2D diagram, right? So then most diagrams that we plot are actually internally reversible or approximated as internally reversible, and so therefore we can calculate the heat for a process by calculating the area under the curve on a TS diagram. So T and S, and let us say state 1 and state 2. So let's say that this happened along that process. Then the area under this curve, this area is equal to Q, which is integral TdS between 1 and 2. And as you can see, this area depends on how the process is and how we go from 1 to 2, and not just states 1 and 2, right? So although the entropy at 1 depends only on 1, entropy at 2 depends only on 2, the heat depends on integral TdS, which actually means that it depends on the path that is followed. And so depending on the path, the area under that curve would be different, and so the heat involved in each of those processes would be different. And so again, heat is a path dependent process, and not a state dependent process. So we can use this very usefully to derive or to calculate the heat involved in a certain process. So for example, in an reversible isothermal expansion, we would have, let's say, state 3 to state 4. This would be a horizontal straight line, and so the heat internally reversible would be integral T ds 3 to 4, and because the temperature is constant, I can pull temperature out and I can write S4 minus S3, right? So if I know the entropy at state 4, know the entropy at state 3, which I will if I know states 3 and 4, then I can calculate the heat required to take the system from state 3 to state 4.